This problem wants us to find the forces in specific members of our truss CE, EF, and CF. So we want to find what I will call FCE, FEF, and FCF. We have CE, we have EF, and we have CF here. Okay, so only 3 of the members are needed. So as a strategy for how to solve for the forces in these 3 members, we probably don't want to use solely method of joints. There's probably going to be a more efficient way to solve for these 3 that will require fewer equations, fewer free body diagrams, if we make at least one section cut. But actually, even before we decide, do we want to do a section cut first, or do we want to use method of joints everywhere, we can look at the external picture and see, are we statically determinant or indeterminate? So based on the supports, A is a pin and D is a roller, we're going to have 2 reactions at A, 2 components of force, and we will have a 1 component of force at D. So there's going to be 3 reaction forces. So the first thing we should probably do is solve the external free body diagram because it is statically determinant, and we're going to be able to find the values of those 3 reactions. So the first free body diagram is going to be the external picture. So I'll call that 1. So in the external picture, just take everything and remove it from the support at A and the support at D. And we also have these 2 applied forces acting on our structure. So we have an 800-pound force and a 600-pound force. And these are 10 feet from each other, 8 feet, and 10 feet. At D, where we have that roller, when we remove the ground is exerting a normal force up. Since the ground is horizontal, the force is then vertical. And I'll call that D. And A is a pin. And like any other pin, we can have 2 components of force, an AX and an AY. We can write now some equilibrium equations now that we have our complete free body diagram for the external picture. It's a rigid body, so we're going to be able to get 3 equations out of this. I'll start in the X direction in picture 1. And we'll see here that we have AX, and that's actually the only force in this picture. So AX is going to then be 0. Now I can make a second equilibrium equation. My second one, I'll actually do my moments around point A as my second equation because it will eliminate AY and AX, though we do know that AX is 0. So if we take the sum of moments around A in this picture, we're going to have, going from left to right, no AX, no AY, but we're going to have a 600-pound times 10 feet moment, and that's going to be clockwise, so negative. And we're going to have an 800 times 18, also negative, plus a 28 times D. So by taking the moment around A, we see that D is the only unknown in this equation. So 2 will be solvable for D. While I'm here, I will sum forces in the Y direction as well. And we'll have our AY minus a 600 minus an 800 plus D. So we can take, well, equation 1 already is telling us AX is 0. Equation 2, the only unknown is D. So D is going to be 729 pounds. And it's a support, so I'll put its direction is up, which it has to be for this one. And our third equation, now that we know the value of D, we can find the value of AY. And AY will be 671 pounds. And it's positive, so it's also turns out to be up, but AY could have been up or down. So the support reactions have been found, and we're going to see this will help us when we go internally to find the forces in the desired members. So now we can go back up and actually start to solve for what we're looking for. Remember, we want the internal forces. This is just a means to an end finding these support reactions. We want EF, CF, and CE, where the red dots are there. So one thing we could do is we could do a pin diagram at D and then start working our way from right to left, and we would be able to solve for our unknowns. But along the way, if we started at D, let's say we would have DE and CD, which we're not asked to find. And we really don't want to start at pin E, F, or C, because if we see, they're each connected to more than 2 members. So starting there, just algebraically, it's going to be tougher to start there. We're going to ultimately need more equations, and we're going to be developing more unknowns. So instead, I would start this with a section cut. So our goal with the section cut is, at least as a rule of thumb, we don't want to cut through more than 3 members, because the free body diagram we're going to be creating is going to be a rigid body, which means we'll get 3 equations out of it. So if we cut through no more than 3 members, we're going to create a solvable system in and of itself. And ideally, we would cut through as many, if not all, of the members that we're interested in. So if we take a look at the bridge, how we can make a section cut here, can we make a cut that goes through all 3 of the members, but only goes through those 3 members so that we're not making extras? So if we try and make a cut like that, it could come in like this, and that's not really going to work. So that's no good. We don't really want to come and cut back on ourselves, and then we're going through another member anyway, so that's not really going to work. But if we keep looking at it, there's no one cut we can make that goes through only our 3 members and no others, and doesn't kind of backtrack on itself. So I would say is the best we can do in our cut is we can cut through 2 of our members, and then we will have another step to get that remaining member. But at least with this section cut, we can get 2 members. Now, again, what we want to do is, if we see with this cut we're making, it goes through EF, CF, and BC. We were not asked to find BC, but we'll see it during going along the way. And what we want to do is take everything to one side of our cut or the other. So as a rule of thumb, I would want to take the side that has less going on. So that would be taking everything to the right. So this, in the green, is going to be our section cut. So I will call this cut 2, and that will be our second free body diagram then. Now, I could have taken everything to the left side of that cut instead, and that would be fine. I'm still going to see the same forces. It's just there's a little bit more going on. I have a pin. In this problem, it's probably about the same. We're not saving that much effort by taking the right side over the left side. All right, so picture 2, I am drawing basically what's in that bubble, the side of the section I am keeping. So what I'm doing is kind of virtually separating the truss out between everything to the left of where I made that cut and everything to the right. And now the things I cut through, since they're not attached anymore, I can see the forces that are in them. So everything that's still intact, I'm going to copy exactly in this picture. So we see here CD, CE, ED are not being cut through. I copy them down exactly, and I'm going to copy all the forces acting on those pieces or those joints that are still intact. So C is still intact. I copy exactly that 800. I'm going to copy the reaction at D. Now, again, I did the external picture for a reason, because we know that D is 729. So in this picture, I'm going to put its value and the correct direction, which it did turn out to be up, so that's okay. And I know that this is going to be 10 feet in the vertical, and C to D is also going to be 10 feet. Now I can see where I cut, just for kind of illustration here, I'm going to keep some of the beam, but I cut through the beam, and that's what's being exposed also in this picture. So that's where my cut are these kind of squiggle lines, and out, I'm going to be assuming tension is the force that was in those beams. So now I can see FEF coming out of here. I cut through BC, I can now see FBC, And coming out from here, I can now see FCF. EF and BC are both horizontal. CF is going out at an angle here. And I'll just put the ratio triangle. It's not going to be a nice integer here, but it's going off. This is going to make a 10, 4, and root 116 triangle. I could just find the angle as well. I'll stick with a ratio triangle here, even though it's not the prettiest one. And finally, I'll just copy down some of the points. All right, so picture 2, the section cut is now complete. And if we look, I've introduced 3 new unknowns in the section cut picture, which are going to be those internal forces in the 3 beams that I cut through. So picture 2 is going to give me new equations to create. So I can make a equation 4, which is going to be, well, I can do it in any order. I'm going to make this one a sum of forces in the y direction, picture 2, because in the y direction, only one unknown is there, the FCF. So I'll have a negative 800 plus 729 plus 10 over root 116 FCF. And I'll be able to solve that easily for FCF. Now, I'm going to go with a moment, and I can take the moment around C. And that's a good location in this picture because it eliminates FCF and FBC if I do that. So taking the moment around C and the 800-pound force, I am going to have 10 FEF, and I'm going to have plus, and that's going to be counterclockwise, so positive, plus 729 times 10 as that equation. And I can right now see that the 10s are going to drop out, but I'll handle that in the solve step. And finally, I can have an equation 6. I'll write it over here. Last one is, I have different options I could do. I could actually take the moment around the point F would be one option, because that way FEF and FCF would drop out. So I actually can do that. I can take the moment about any point, whether it's on my structure or not. But just for consistency of what we usually do, I'll do a sum of forces X. There'll be a little bit more algebra doing that, but we know we're making a linearly independent equation. So in the X direction, I have a negative FEF, but by this time I'll know its numeric value of FBC, and minus a 4 over root 116 times the FCF. So we will know the values of CF and EF by now. So actually BC is the thing we're not going to know yet. And also in the X direction, that should be it. So FEF, FCF, FBC, the applied forces are not in the X direction. So coming down here, using equation 4, by that design, FCF was the only thing we did not know. So FCF, we get a 76 pounds. Now here, it's an internal force in this 2-force member, positive because I assumed tension by drawing everything out. Positive indeed means that assumption of tension was correct. So positive 76 pounds, and we're in tension. And FCF is one of those values that we were looking for. So I'll just mark it so we remember. In equation 5, FEF, solving, is negative 729 pounds. That turns out to be in compression. And EF was also one of those values we were looking for. And then equation 6, EF we know, CF we know, so BC is the last unknown. We technically don't have to find it. We were not asked for it. But solving along the way, it's 701 pounds. We might need it in the next step because we're going to see there's still one remaining unknown from the find. So we have BC is positive 701 in tension. So CF, EF we found. CF and EF have been found. So the last thing we need is CE. So we're going to need another free body diagram because we need to generate more equations at this point. Now we could do another section cut where we are cutting through CE this time. So that would be one possibility. So for example, we could make a cut that would go through, let's say, EF, CE, and CD. That would be okay. And then take everything to one side. That's one possibility. Or we can mix and match pin diagrams is also fine. So what I'm going to do, I don't know if it's much easier or not, is I'm going to make a diagram at pin C and use method of joints once. So this is going to be a particle equilibrium. And I'm choosing C because at this point we know BC, we know CF. So there's only going to be two things we don't know, CE and CD, in this picture. So we will have definitely a solvable system at this point. So it's up to you the method you want to use, but we want to reduce the number of pictures, the number of equations we have to deal with, certainly. So a pin diagram at C, we have that applied 800 pounds down. We have FBC to the left, assuming tension, which we always want to do. FCD to the right. We will have here FCE, which is ultimately what we care about. And then we have here FCF, and it's going at that triangle that is that 10, 4, root 116 triangle. Make it a little bit bigger. Okay, and that is everything happening at C. Again, we already know CF, we already know BC, so those remaining, we only have the two unknowns left. So we can come down here and make a number 7. Remember, what do we care about? We want CE. So I'm going to start this by summing forces in the y direction in picture C. So I have FCE, which is ultimately what I care about, minus 800 plus 10 over root 116 FCF. Again, FCF we know from previously is that 76. So we can solve this for that remaining unknown. I'll just point out again, when I'm writing all of my free body diagrams, those internal forces I am leaving as variables even once I know what their numeric value is. Because to be consistent of tension positive, compression negative, this is going to be the easiest way to do it, is we keep drawing them assuming tension. Even once we know that is wrong, we need to stay consistent with all of those values. So I'm always writing it in variable form in the free body diagram. I'm using that free body diagram to write my equilibrium equations. It's not until the solve step that I actually will substitute in the numeric values for ones I already know. Now, for internal forces, that's how I do it. Again, for the external forces like D, we found that first, and yes, in subsequent, like in picture 2, I just wrote it as 729 in the correct direction. So external forces, put those in the correct directions with their values in subsequent internal free body diagrams. But for internal forces, leave them in variable form, assuming tension, and wait to substitute anything until that solve step. So in equation 7, FCE, the last unknown, is going to be also a 729 pounds. But this is in tension. And that was the third and final unknown we were searching for in this problem. Now, notice what I didn't do. I didn't even use equation, the sum of forces in the x direction in picture C. I don't need to, in that I already know everything I need to know, everything I was asked. However, if I did do that, I am not generating this is not going to be a new linearly independent equation, but it still must be true. So it might be worth checking. So this would be from the picture FCD minus FBC minus 4 over root 116 FCF. Right, those are the only things with x. If we came down to the solve step, if we substitute in our values, well, the left-hand side is 0. The right-hand side, now that we know all the values, if we check this out, we had better get 0 also on the right-hand side. Or, again, with a little bit of rounding, we might get a very, very small number that's very close to 0. So all 8 tells us is that it should be 0 equals 0. It should just be true at this point because we've already solved for these 3 unknowns previously. But if we're getting 0 equals 7, that's telling us that something is wrong. We either did math wrong somewhere or maybe our modeling is wrong. But if we get 0 equals 0, it's a good check for consistency that it appears as though we're going on the right path. So number 8, I did write it out. It was not a new linearly independent equation though. So we found the 3 unknowns that we were searching for. We were able to do it with a section cut and a pin diagram. And if we look in total, we generated really only 7 equations that we really had to have in order to solve this. We actually could have maybe done this in an even more efficient manner, but by making that section cut, we really reduced the potential number of free body diagrams and equations that we were going to need. And we didn't need to solve the pin diagram for every joint, because in this case, we were not looking for the force in every member, just the force in these 3 particular members.